amplifier design, and I'm currently working as a lead application engineer at Keysight. With me here is Tom Winslow. Tom is a distinguished fellow at MACOM, and today's webcast will be on designing for stability in high-frequency circuits. The goals for this webcast will be to learn techniques that will help you identify and solve stability problems in the design phase early on, using a new impedance probe called the WS probe, and also to see an example of how this probe actually works in real life, so you can avoid, when you get into the lab with your circuits, having a spectrum like this pop up. That is, of course, unless you're trying to design an oscillator instead of an amplifier. I wanted to start the webcast off with a question, which is, why should you design for stability in high-frequency circuits in the first place? You know, in the past, RF and microwave engineers used to go into the lab, they would add some bypassing and loss, and they could stabilize their circuits just fine. So why add yet another constraint to the design process up front? Well, if you look at what's going on across the wireless industry, you'll notice that systems are generally getting more complex, and at the same time, they're moving higher in frequency. And because of that, the circuits themselves are getting more integrated and compact using devices that have more gain. Well, when you look at instability, you know, fundamentally, it arises from a combination of gain and feedback. So today, the devices have more gain because the transistors have higher FTs, and there's more feedback because integration at higher frequencies means more coupling. So in the past, you could just go into the lab, make some adjustments, and eventually stabilize your circuits, but you can't do that anymore with the level of integration that's around today. You know, you need to really master stability by truly understanding the root causes before you build your design. And in today's webcast, we're going to show you how to do that. Let's start with the keystone of high-frequency stability analysis, which is Rowlett stability factor. This is called K. If you're an RF and microwave engineer, this technique was probably your first encounter with stability, and we've all learned that if your K is greater than 1, essentially your circuit will be stable. But unfortunately, there are a lot of caveats to this. You know, I put an example here of a ring oscillator, which is a well-known example, and it's got a K factor that's much greater than 1. But it can be proven to be unstable using a normalized determinant function. We'll talk more about that later. So Rowlett's stability factor is not, in fact, a complete characterization of stability. In fact, if you read the original work, there's a note that implies that this analysis is only really valid for stable unloaded networks. Basically, this started out as a measurement technique, and it applied to networks that can be measured. So from there, you can infer if any other loads will make it go unstable, but it doesn't quite stretch to simulation. The truth is, K-factor is just one of many stability approaches out there, and it has caveats. Probably the biggest challenge for designers is actually not a lack of approaches, but too many approaches, all with their own strengths and weaknesses. And if you dig through the papers on the subject, you'll find techniques that eventually trace back to the work done by a few great engineers at Bell Labs, namely Bode, Nyquist, Black, and a few others. And for each approach, there are multiple simulation techniques to derive the figure of merit. Usually, each one requires some different kind of setup and stimulus condition to get the answer, and then when you compare them, you still might get conflicting information like we saw with K-factor. So with all of these techniques, it's very confusing, and speaking from my own experience as a circuit designer, stability is one of those things that really kept me up at night because it's hard to feel confident when you have all of this information. So what do you do? Okay, well, at the risk of giving away the ending, I want to tell you what all this is building to, which is the concept of a general stability probe in the simulation tool. This probe can allow you to apply just about any type of stability analysis technique to your circuit in a very straightforward manner. And the probe is nicknamed the Winslow probe because it was developed by my co-presenter today, Tom Winslow from MACOM. Tom had been struggling with designing these high-frequency circuits for a long time, and he was looking for a simpler approach, so he developed this probe. And he worked with Keysight to get it into our tools. So today we're going to show you how to use the probe, and I'll even provide an example workspace that walks you through the techniques we cover in the webcast today. So here's the agenda. The big goal is to help you understand and simplify stability analysis complexity with the Winslow probe. But before we get there, you'll have to have some background so that you can appreciate the power of this technique that we're going to show later. We'll start with a review of feedback systems and see how assumptions and simplifications in the theory can lead to results which aren't always rigorous. And from there, we'll go back to fundamentals to try to understand what is rigorous in terms of approaches. And then we'll show you how you can effectively apply multiple approaches at once using a simple probe that gives bidirectional impedances inside your circuit, and then we'll show an example of how to use the technique on a real circuit design. So let's get to it. So I know some of you are beginners in this space, and I thought it would be best to start by reviewing some basic concepts to get you up to speed. If you open up an undergraduate circuits textbook, you'll probably find this system-level framework in there for feedback analysis. It basically shows how to combine an amplifier with a feedback network and to derive the closed-loop transfer characteristic called ACL. In the denominator of that transfer function, there's a term which multiplies the amplifier and feedback terms. This is called the loop gain. And if this loop gain goes to 1, the overall transfer function then goes to infinity, which means essentially the circuit is oscillating. If you look a little closer at the transfer function, you'll notice that it's really an S-domain equation. And S-domain equations can be factored into zeros and poles. Through the Laplace transform, the poles ultimately map to exponentials in the time domain. Hopefully everyone remembers that from school. Now, the exponentials can either shrink or grow to infinity depending on the sign of the pole. Poles with negative real parts decay in the time domain, and poles with positive real parts grow. So you can plot real versus imaginary S on a graph, and if the poles are in the left-hand half of this S-plane, they're stable, while if they're on the right half, they're unstable because they result in growing exponentials. If you're designing an amplifier, you of course want to avoid the right half plane. So how do you derive this loop transfer function for your circuit? Well, you can do that using a simulation, and what you'll get is a response. So how do you take some response curve that comes from a simulation and figure out whether there are unstable poles in it? You can use something called Cauchy's principle. This is shown on the left. And this states that if a closed contour in the S-domain passes through any transfer function, the output will encircle the origin clockwise the same number of times as the zeros minus the poles. It's kind of a detailed derivation, and I only have time to cover it briefly here, but that's the conclusion. So we can apply this to the closed loop transfer function for the feedback system by just looking at the denominator. When that has a zero, the function has a pole. There are some derivations and math tricks behind this, but basically you can assess the entire right half plane of your transfer function by just sweeping frequency from 0 to a really high value. Then the output you observe will encircle the origin based on the difference between the right half plane zeros and poles. If you can ensure that there are no poles, either by knowing the stability of the individual blocks or by constructing a function that guarantees it, then the number of encirclements is the zeros in the right half plane, and you can assess stability based on observing that. All right, let's talk about how to simulate loop gain. For this webcast, I put together a simple model for an amplifier and feedback network. For the amplifier, I've got a basic transistor that has a controlled current source inside of it, along with some parasitics. And for the feedback network, I've got a termination set and an LC across the transistor. Those are hopefully realistic enough to be instructive, but simple enough to allow you to follow along with my analysis. Now, both of these blocks are stable on their own, and here's an example then of one way to simulate the loop gain. I'll use a component called OSTest in ADS, which is a special kind of termination, where the forward wave traverses out one side of the component and the returning wave then comes back into the other side of the component. And along those lines, the loop gain is then just S11 of this termination. When I apply the OSTest component to this network and do a very broad frequency sweep, then S11 represents the loop gain between the breakpoint. And I can evaluate stability by looking at the number of clockwise encirclements around 1. Those will represent the right half plane zeros in the denominator. So for this case, the loop gain does not encircle 1, so the system is implied to be stable. Now, there are certainly simplifications that go into the approach. First off, the loop was physically broken and terminated with some arbitrary impedance, and that's not realistic. Second, the OSTest element runs the tests in one direction only. In real life, the signals travel bidirectionally. They go forward through the feedback network, and they also go backwards through the amplifier. And third, this breakout of the amplifier and feedback block was quite imprecise. Really, the amplifier is just the transconductance block, not the entire transistor model. So there can actually be feedback locally inside the transistor that really should be included in the F block instead of the A block. So these assumptions can cause that conclusion that we just drew, that the circuit's stable, to be incorrect. Now, over the years, a lot of smart engineers realized this, and attempts were made to improve the technique for loop gain. So next, I'll briefly review a few of those improvements. The first obvious flaw is that with loop impedance, the way you terminate the loop can actually change the loop gain. Now, a fellow named Middlebrook developed a measurement technique to reduce this sensitivity to impedance and location, and this technique was called double null injection. One note for you measurement historians out there, Middlebrook actually used the Hewlett-Packard 302A wave analyzer to measure his loop gain, and Bill Hewlett also employed feedback techniques extensively in the design of this series of instruments. So, in other words, loop gain concepts were used to design the measurement equipment that was then used to later measure loop gain. So I think that's pretty cool. Anyway, this concept is pretty fundamental, and in simulation you can emulate the original measurement technique by applying two test sources anywhere in your feedback loop. So one voltage source and one current source, and then you can observe the return. Next, you combine them into a single loop gain value, which is deemed then independent of breakpoint location because of the dual nature of the stimulus. And here I applied this technique to the same test circuit that we had earlier, and you can see that the loop gain does in fact encircle 1, implying now that it's unstable. Now, in both of the previous examples I showed, the way that the signal traveled through the loop was assumed to be one directional. There have been several attempts to recompute loop gain bidirectionally, and what's shown here is probably the most commonly cited technique. This is done by Paul Hurst. Essentially, you can represent the amplifier and feedback as bidirectional gain blocks, then you can combine them in parallel and derive the loop gain directly in terms of Y parameters of each block. For the working example, I did this by computing Y parameters of the two blocks individually, and then I ran them through the formula, the Y parameters, and the result now does not encircle 1. So lucky for us, our amplifier is again stable. Okay, that covers the basics. In the next section, we're going to revisit some of the fundamental concepts that underlie the amplifier feedback framework that I presented in the last section. Just to recap, in the last section I tried 3 different analysis techniques on a basic example, and I got conflicting answers. And here I threw in k-factor too, just to confuse things more. So the big question is, of all these techniques, which one's correct? It's not clear at all. To make matters worse, each technique required a different simulation setup. K-factor had me terminate the circuit and analyze it. OSTest had me add a component. Null injection required 2 sources, a copy of the circuit, and an AC simulation. And the bilateral model required me to characterize the amplifier and feedback blocks separately, then combine them mathematically. Whew. So you're probably wondering if there's a better way to do this analysis, and there is, but before we get to that, we need to answer the question, which of these results is correct? And to do that, we'll need to dig more into the fundamentals. Now, when I say fundamentals, I really mean Hendrik Bode's original work from the 1940s called Network Analysis and Feedback Amplifier Design. This is the classic book on stability. So I want to revisit this to understand some fundamental measures of stability and see how these can be applied today, because really the techniques I showed in the last section originally evolved from these fundamentals. In his work, Bode grappled with the same challenges regarding stability that we just ran into, and the big question was, how can you have a rigorous characterization of whether a system is stable? So Bode examined in his work how instabilities manifest into a system. He described really 2 views of a system, one as a set of meshes on the left, and the other as a transfer function on the right. And he used 2 measures, driving point impedance and return ratio, to characterize the systems. I've put the text from Bode's book introducing these measures on the right-hand side of this slide. So let's start with the return ratio or return difference. Basically, if you view your system as a transfer function, Bode showed that you can look at the way that a transconductance element inserts itself into the network to determine the system stability. So he defined a return difference and a return ratio as kind of fundamental versions of the transfer denominator and loop gain terms that we just looked at in the last section. And specifically, he defined these as ratios of the system determinant to the same determinant with the transconductance removed. So basically, he normalized the active system to an equivalent passive system, which he knew was stable. Bode also presented another view of a system as a set of nodal equations, the solution to which is the steady state voltage resulting from the driving currents. So in essence, each node in the system can be analyzed for stability by observing the way in which the node enters into the overall system determinant. So we define driving point impedance as just that, the ratio of the system determinant to the same determinant with the node itself removed from the matrix. Let's compute the return ratio for the example that I showed earlier. To do that, I need to access the internal transconductance inside of the transistor model so that I can turn it off. And I implemented that in ADS using a variable called sourceOn, which I could then set to 0 or 1. After that, I took 4 high impedance probes and I put them across the terminals of the transconductance element to get the admittance matrix across the transconductance. And then I took the ratio of the admittance determinant with the transconductance on to the admittance determinant with the transconductance off. And that is the return difference. Plotting that on a polar plot finally shows that the circuit is unstable, and this is something that we can have a good deal of confidence in. Let's compute the driving point admittance at the input node for the same example. The reason I'm using admittance instead of impedance is because it's a little easier to analyze this term for stability. So to compute the driving point admittance, I need to take the system determinant and normalize that by the same determinant with the node that I'm interested in removed from the matrix. So let's assume that we wish to analyze the input node here. Well, if we simplify this circuit to a 2-port network, removing the input node means that we would remove the first row and column of the matrix, which just leaves one term, Y22, in a 1-port matrix. So the driving point admittance is that 2-port matrix determinant over Y22. That's if we're analyzing, of course, the input node. Now, we can analyze this result a little bit differently than return ratio. Instead of looking for encirclements, we're actually looking for negative real admittances that have imaginary parts that cross 0 with a positive slope. That's called Kurokawa's condition for oscillation. We're actually trying to find places where the circuit has a solution which is independent of the drive from the rest of the network. And I noted in this example it encounters Kurokawa's condition at around 4 gigahertz. So the conclusion is that the circuit is unstable there, which agrees well with the return ratio computation that we did in the last slide. Now, as you can probably guess, both return ratio and driving point admittance are academic. For modern circuit design, we need more practical approaches because most designs have lots of nodes and they've got lots of transistors. So the modern approach for return ratio is called normalized determinant function. Basically, what this says is you can generalize the return ratio concept if you have multiple active sources by simply expanding the order of the matrix accordingly. Now, in the working example, I only had one active element, so in that case, the NDF just equals return ratio. But in this case, I'm showing here, I've got an expanded example where I added another transistor in parallel with the amplifier and feedback. So now I have 2 active elements. In this case, I'd need to access the intrinsic transconductive sources for both, which effectively doubles the number of terminations. And then I would look at the normalized determinant function and again count the encirclements, just like I did for return ratio. Just one note here, in ADS, the built-in determinant function has been improved specifically to support this type of NDF calculation. And there's also a new function that automatically computes encirclements, which makes analyzing normalized determinants and other metrics much easier. Now let's look at a modern approach to figuring out driving point admittance, and that is called an auxiliary generator technique. To find this in simulation, you can apply a current source to a node, and then you inject a current and you monitor the voltage across the same node. The driving point admittance is just the current over the voltage. So here in our working example, I applied a current source to the input side, and I used this to derive the driving point admittance, which agrees with the earlier mathematical result that I got before. So now that you know the math behind return ratio and driving point admittance, I wanted to walk through one final loop gain derivation. This is called true return ratio. I think it's actually a pretty clever way to compute the loop gain, attempting to adhere to the original concept of return difference. And this was done by a fellow named Michael Tian. Basically, what you do is take an amplifier block and define the feedback around it to be a short circuit. You can combine the feedback in parallel with the amplifier like I showed earlier. And from there, the Y matrix becomes greatly simplified. Since the output voltage is just equal to the input voltage, that becomes a one port. And the determinant of a one port is, in fact, the value itself. So you can remove the active parts mathematically, and what you're left with is the return ratio from the Y matrix. Now, despite the name true return ratio, if you really dig into this, I still consider it a loop gain calculation, and I'll show you why that is in the next slide. So let's apply this true return ratio to the working example. And to do that, we use a double injection technique, kind of similar to Middlebrooks, to derive the Y parameters. So here I put the injection point outside of the feedback. It's just a short between the input and output. But when I compare the true return ratio with Bode's return ratio for this example, I found out two are different. So what's going on? Well, in short, the example that we've been using does not adhere to that idealized gain block assumption that was made in the derivation. To make the true return ratio actually match Bode, I needed to simplify the transistor model as shown below to ground the source and remove the internal CGD feedback element. And when I did that, the true return ratio then exactly matches Bode's return ratio. And that's why I said before that I still consider this computation a loop gain method rather than sort of a more rigorous method. This is just illustrating the fact that there are often assumptions that occur in loop gain approximations which might change the result. Now that said, even though the curves on the top do not perfectly match, if you look closely at the area where the circuit transitions from stability to instability, the true return ratio does in fact predict that accurately. So I don't want to discount that approach completely. In fact, let's dig a little bit deeper into the true return ratio. It turns out that you can also relate the true return ratio to the driving point admittance. Bode showed that the driving point admittance is just the sum of the Y parameters in a collapsed network around the node under analysis. Well, if you look at the true return ratio, it's also fundamentally derived from the admittance matrix. And you can define another term called open port admittance, kind of representing the admittance external to the loop. And with that, then you can represent driving point admittance as the product of a loop gain term and an open port admittance term. I like this relationship because it intuitively makes sense, and I think it returns some rigor back to the loop gain computation. In other words, loop gain itself isn't completely rigorous because if your analysis point isn't inside of an unstable feedback loop, you won't see the instability. But if you include adjacent admittance terms on either side of the node that you're monitoring, then you can detect negative admittances nearby, and that makes this loop gain technique much more rigorous. So in short, I still think that loop gain is a really valuable design tool, and the reason is that it points to something potentially obvious in your design that you can analyze or fix, mainly feedback loops. I'll show this later on in the demo, but once you start looking for these loops, they tend to appear everywhere in your circuit. If your NDF is unstable, what do? There's actually not much action that comes out of having an unstable NDF. But if your loop gain's high, a good designer can usually figure that out. And so the pairing, I think, of loop gain with NDF or driving point analysis is pretty hard to beat because the combination of the two provides both rigor and also the ability to troubleshoot. So we covered a lot in this section, but in summary, the fundamental concepts from Bode's era can be adapted to modern times. Return difference can be applied to complex networks using the normalized determinant function. This is global and rigorous, but you need access to the intrinsic source, which can be a problem if you didn't create your own model. And despite its rigor, NDF really gives no indication for the cause of instability. Driving point admittance is easily implemented in simulation using an auxiliary generator, and while the technique is also rigorous, it's local as opposed to global, meaning that it only applies to a single node. So you might miss something. If you want to analyze every node in your design, then the simulation becomes a lot more intensive. as you can only typically analyze one node per simulation. And finally, loop gain is a great design tool, but it doesn't have the rigor of the other two methods. It's best if you can combine them, but doing that requires multiple simulation benches and, of course, multiple techniques. So far, we've reviewed a number of analysis techniques for loop gain, return ratio, and driving point at minutes. Now that we've got a decent arsenal of methods at our disposal for stability analysis, the problem now becomes simulation complexity, meaning that just deriving these metrics in simulation can be really costly and quite prohibitive. In this section, we're going to look a little more closely at a technique to simplify that. Recapping the problem, for each one of the analysis techniques discussed, a different simulation methodology is needed. For the OS test, you need to insert the component. For some loop gains, you need dual stimulus. For NDF, you have to add terminations and toggle your sources. And for driving point at minutes, you need an auxiliary source, et cetera, et cetera, et cetera. So how can we simplify this? Well, to answer that, I want to bring up a pretty old concept that goes back at least 30 years, and that's the idea of using a probe to derive impedances that can be used for stability computations. If you think about it, many of the techniques that we've seen so far have really just been clever ways to derive stability metrics from Y parameters. So what if a probe could be used to give you those Y parameter inputs? Then it would just be a matter of performing the right computation to get the stability measure that you're interested in. Well, something like that's been in the tool for a long time. In ADS, this is called S-probe, and the output is actually the bidirectional reflection coefficients of the network. So in theory, you can insert this component in the loop and use the gammas to derive the impedances and admittances you want. But it's not very widely used today, and you might wonder why. So to talk about that, I want to pass the ball now to my co-presenter, Tom Winslow. Tom is a distinguished fellow at MACOM, and he's been doing high-frequency circuit design for many years. And I think it's safe to say he's run into a few stability problems along the way. A little while back, Tom reached out to Keysight. He's been a long-time user of our tools, and he showed us what he's about to show you. And we were compelled enough by his presentation to add his work to our design tools. So, Tom, go ahead.
As designers, we push the limits of our processes and design capabilities. As part of this, it's important for designers to be able to in situ calculate the impedances within their circuits and the resulting stability. So without perturbing your circuit, and for any given node within your circuit, you want to be able to compute the bidirectional looking impedances. Well, why? Well, the bidirectional in situ impedances tell you what your load lines are for designing power amplifiers. The in situ bidirectional impedances can tell you how well your circuit is matched at a given node. If you compute the product of the bidirectional looking reflection coefficients, you now have the classic stability index. The original S-parameter probe was proposed by Ken Wang at TI, published in 1992. The original S-parameter probe was developed specifically for oscillator analysis. Now, the S-probe that you find in ADS is a modified version of Ken Wang's approach. The problem with all current attempts at in situ impedance probing is that they either perturb your circuit or they're mathematically unstable and thus inaccurate in the presence of detectable amounts of feedback. But this has all been resolved with the new WS probe in ADS 2020. This new probe approach has been fundamentally reformulated and provides absolutely accurate bidirectional impedances, bilateral, unilateral loop gains, open port impedance, series loop impedance, and the driving point impedance of a given node under arbitrary levels of feedback. And also, this new probe can be used in ad hoc pairs to analyze arbitrarily defined subnetworks within your overall circuit. And for this, think chain analysis, where you define probe pairs and the probes acting together as a pair can completely analyze any subnetwork block between and outside of the given probe pair. This full analysis capability, the full analysis capability of the probes now has never really been so easily available before in any design tool. So to demonstrate this, we have a very simple passive circuit demonstration that shows the difference between the behavior of the old S probe and the new WS probe when subjected to feedback within a circuit. So if you study the circuit shown, you see it has obvious low frequency and high frequency asymptotic behavior that can be understood largely by inspection. So from the probe's perspective embedded within the node, the low frequency looking source impedance will basically look like a 50 ohm resistor in series with a 4 puff capacitor. In the load looking direction, you'll see that the probe will see a 20 ohm resistor in series with an 8 puff capacitor. The half puff feedback capacitor now at very low frequencies or asymptotically low frequencies becomes a very high impedance, and it breaks the feedback loop around the probe. In this slide, the performance plots show that both the S probe and the WS probe predict the same bidirectional impedances when the feedback is asymptotically approaches 0 at very low frequencies. And this partly explains why the old S parameter probe has not really been abandoned after a quarter of a century in circulation, because basically it's asymptotically correct in the limit of 0 feedback across its terminals. The problem shows up when there is a detectable amount of feedback across the probe's terminals. The high frequency asymptotic behavior of the circuit looks completely different. The inductors become very high impedances, and from the probe's perspective, we see a loop formed by 3 series capacitors, where the half puff capacitor is now closing the feedback around the loop. At high frequencies, there are no resistances within the loop, just the 3 capacitors, because the 2 external inductors outside of that loop become very high impedances. The sum of the 3 capacitance is equal 0.42 picofarads by inspection. And you can call this the loop impedance. If you look at the old S probe prediction of the bidirectional looking series resistances, they go into negative values above 100 gigahertz. And this is completely non-physical. The new WS probe accurately returns 0 resistances in the source and load looking directions. And this is completely and necessarily predictable by inspection, given that we are asymptotically dealing with a closed loop composed of 3 series capacitors around the terminals of the probe. Also at high frequencies, you see the old S probe predict that both bidirectional looking reactances asymptote to 0, which is equivalent to 0 capacitance, which is also completely non-physical. So the old S probe is saying that it sees the high frequency source and load looking impedances to be composed of negative resistances and 0 capacitances, which is completely wrong by inspection. The new WS probe analyzes the network that it is embedded within, and it does a network reduction and accurately decomposes the loop impedance. Now, how it does this is beyond the scope of this webinar, but this net loop impedance that it calculates behaves exactly like the 3 series capacitances that sum up to a total of 0.42 picofarads. The probe can calculate, again, this is beyond the scope of the webinar, but it can calculate the equivalent bidirectional looking impedances, the sum of which must be equal to the total loop impedance. I can't get into any details about how it does all of this, but if you look at the high frequency range of the series capacitance plot on this slide, you will see that the bidirectional looking capacitances show up in series to the expected total capacitance of the closed loop 0.42 picofarads. Now, I strongly recommend that you build and study the circuit in ADS 2020 and drop the WS probe and the S probe in the center of the node as shown in the slide and run the simulation. Take the bidirectional impedances provided by the probes, convert those impedances into the series RRC equivalent models, and study the example. You will see that the new probe provides sensible and accurate results that can be understood by inspection of the circuit. The old S probe clearly provides nonsensical results when the feedback becomes detectable and substantial. And it's exactly when feedback becomes aggressive in our circuits that we want these impedance probes to be their most robust and their most accurate for both impedance analysis and stability analysis. So it all comes down to the mathematical basis of the probe and how it deals with feedback. This new WS probe can provide an unprecedented amount of analytic power for designers, and I recommend you give it a try. And back to you, Matt.
Thanks, Tom. So with that seemingly little tweak to the S probes, we now have a really powerful stability analysis tool at our disposal. Why is this new probe so powerful? Well, because you can run one single simulation and use the result to compute pretty much every figure of merit that we've shown so far in the webcast and more. All you need to do is put the probes in nodes in your design that you're interested in analyzing, and then you just run a simulation. And from there, The outputs of the probes, basically Y parameters, can be used to compute everything without changing your setup. The probe doesn't disturb or change the behavior of your circuit, it just accurately provides the impedances or admittances that it sees across its terminals, regardless of the feedback around it. So to illustrate, I took the example we've been working with and I put two WS probes around the amplifier, and then I ran a simulation in ADS. And in the data display, I took the probe outputs and either directly plotted them or I ran them through simple functions. And I derived all of the stability metrics that we discussed today from just one single simulation. What I'm showing on the right is a comparison between the results. The probe data is red, and the earlier simulation data that I did before was blue. And the results you can see here agree almost perfectly. So I wanted to look at this a little bit more closely. What I mean is that this probe simulation emulates the earlier OSTest simulation because I can pass the probe output directly into a function where I specify unilateral loop gain and 1.1 ohms termination impedance like earlier, and the result from this equation perfectly matches the earlier OSTest simulation we did. Better yet, I can also reverse the OSTest component virtually by just changing a function input. Instead of UNI, I put REV in there, and I can also virtually run OSTest on the output node too, because there's also a WS probe on that node. So to recap, I can replace 4 OSTest simulations that I'd have to do separately, 2 nodes forward and reverse, with a single WS probe simulation. That's pretty good, but we're just getting started. The same single WS probe simulation can also compute Middlebrooks loop gain. Remember that for the double null injection, we needed to run 2 simulations or make 2 circuit copies, one for the voltage injection and one for current. The WS probe can do this in one simulation on one circuit and for 2 nodes, since there are 2 probes in the circuit. So add 4 more simulations to the ones that can be replaced with just one of these WS probe simulations. We can also compute the Hurst loop gain using this set of probes as a pair. Remember, for the Hurst case, we actually separated out the blocks and computed the individual Y parameters, and then we combined them in a formula. Well, now the probes can be used to virtually separate these 2 blocks of impedance, and the function blockcalc computes the loop gain. Another simulation in test bench has now been replaced by the WS probes. And while we're at it, we can also do the total return ratio loop gain computation from this same simulation too. Similar to Middlebrook, this required 2 simulations for each node because it was a double injection. Now it's done with just this same WS probe simulation. So there are 2 probes, so again we can replace 4 total return ratio simulations with just 1 WS probe simulation. So this is, we're starting to get some momentum going here. There's still more. We can use the probes to construct a multiport Y matrix, which can then be used to virtually compute the normalized determinant. This is equivalent to having arbitrary sets of high impedance probes in your circuit. And with WSP, you can actually be quite selective about what probes you want to build the Y matrix with. So this can be useful if your matrix is really big and you want to down select to a subset of nodes that you want to compute NDF with. So here's another simulation that's simplified by these WS probes. And last but not least, we can use the probe output to derive the driving point admittance. This is the equivalent of having a current source at your node, injecting a current, and monitoring the voltage across the same node. And remember, for the auxiliary generator technique, you can only analyze 1 node per simulation sweep. With the Winslow probe, you can analyze any number of nodes at the same time with just 1 single simulation. So this simple case replaces 2 driving point injection simulations with 1, but with more nodes it could really be a much larger win. If you're keeping a conservative score here, on this simple example I've shown, it would take a total of 14 simulations and test benches to derive the stability metrics computed here with just 1 single WS probe simulation on 1 test bench. And the more complex your design is, the better these numbers get because there are just more nodes to analyze. And this is just the metrics we've discussed. There are lots of other metrics you can compute as well that are outside of the scope of the webcast. Okay, so it's 14 test bench simulations to 1 Winslow probe simulation. And next I want to run up the score even more. So far we've been discussing small signal simulations, but in many cases you actually want to assess stability under large signal conditions where you're driving the circuit into a nonlinear region. That typically requires a harmonic balance technique. Usually a large tone is used to drive the circuit while a smaller tone is then swept across frequency to assess the gain far away from the large signal. The problem is in most cases the large signal setup required is completely different from the small signal setup. So let's take again the case of OSTest. For a small signal, we just inserted a component and ran this quasi-S parameter simulation. That was pretty easy. But for a large signal simulation, we need an entirely different technique, one where the separate small signal is very explicitly injected into the large signal circuit using a different AC source. Now, not only that, but to assess the correct voltages, we now need to get into the mixing matrix for harmonic balance and index the correct terms to make sure we pick the small tone and not the large tone. So pretty much in every case, the large signal simulation setup for this stability analysis is completely different from the small signal case. And most of the time, it's a lot more complex. So if only we had a way to make it so that the large signal simulation could be the same as the small signal. Well, now we do. For Winslow probe simulations, the large signal stability metrics can be derived from the same probes that were used for the small signal analysis. And here's how I did this with the working example we've had. Basically, I took the same circuit with the probes that I just used for small signal, and I reconfigured the input to allow connection to a large signal source. And then I checked a box in the harmonic balance controller to perform stability analysis, and then I ran a single harmonic balance simulation. And I'm done. Compared with the small signal case, I didn't have to change anything in the data display to view all of the same metrics. In other words, the data format for the probe for a large signal simulation is the same as for a small signal simulation. And here are all the figures of merit from before, just under large signal drive instead of small signal drive. Now, you might notice the results look exactly the same as they did in the small signal test case. That's actually expected because the sources are just linear for this example. But if you do have a nonlinear circuit like a power amplifier, you'll certainly get different results for large signal versus small signal stability simulation. All right, I hope you can see how the WS probe simplifies stability analysis. In this one case that I showed, we just replaced 28 separate simulations that basically required 28 setups with one simulation that required just one setup. And practically speaking, what the probe really does is it puts metrics in your pocket that you wouldn't otherwise have, because obtaining these metrics through simulation is prohibitively difficult. For example, doing a driving point admittance simulation on 200 nodes individually, it's just not worth it. It takes 200 manual simulations, but with WS probes, you just run one simulation and you've got all the information when you need it. Also, the probes can be useful for deriving impedances. So for example, if you're designing an interstage match, it's really useful to view the non-perturbed bidirectional impedances, which is exactly what the probe gives you. The probes can also be grouped together into separate parts to take the two separate parts of the circuit and make them blocks of impedances, which is convenient. So for example, this is how I computed the Hurst loop gain earlier. And we can even group probes into bigger sets as well. That's how I computed NDF. So there's a lot of power and depth inside this one probe. All right, so I've shown you a lot of slides about the probes, and I thought the best thing to do next would be to have you see it in action. So what I'll do is I'm going to play a video for you of a live demo that shows a circuit design example where we use the WS probes to track down some stability problems. The example I'm going to show today is a gallium nitride power amplifier at 1 GHz, which was built using a Qorvo transistor and a device model from Monolithics. So thanks to both companies. What I'm going to illustrate in this demo is how problems can arise if you're not careful about modeling unintended feedback loops in your circuit design. So here's a transmission line based schematic. This is usually a pretty good way to start your design, to build the matching network. And the fundamental amplifier performance looks pretty good. So now it's time to analyze stability. And in the initial design of this circuit, stability was in fact considered. You can see there are resistors on the gate side of the device, and in addition, the DC bias lines have a set of bypass capacitors. Both of these things are good practice for stabilizing circuits. I've added Winslow probes to both the gate and the drain of this device, and what I'll do is run a large signal simulation to get results. And I do that by going into the harmonic balance controller and checking the stability tab, and then I do a broad logarithmic frequency sweep around the large signal. I picked about 200 points per decade. Now, as far as technique,
One thing to note is that this transistor doesn't have the ability to go inside and toggle on and off the intrinsic source. I'd say that's a really common situation. So we can't reliably get to a large signal NDF computation, and that leaves Bode's driving point analysis as the most rigorous option for this scenario. In the data display, I plotted the driving point admittance directly from the probe output term H0. Then I look at the real part and I check for negative values. One trick that I use is to take the minimum of the entire sweep and then I look at the sign of that. In this case, the sign's positive, so that indicates the amplifier is stable. As one last check, I'll look at the total return ratio version of loop gain in dB. Again, this comes directly from the probe, and that's very low, basically 0. So if you did this design, you might think, the amplifier is stable, I'm going to go on vacation, but unfortunately, it's just not that easy. If you look closely at the schematic, you'll notice there are no feedback loops modeled. Everything here is tied to an ideal ground, and there's absolutely no trace coupling, which is not realistic. At high frequencies, you really have to ask yourself, am I modeling all of the loops in my design? Anytime you see a loop gain this low from a simulation, it's very suspicious. So let's look at the physical layout. I've got this loaded into our Pathway VM tool. This is called RF Pro. And if you have an experienced eye for high frequency design, you might start to see some potential feedback loops appear in this. So I ran an electromagnetic simulation of the layout. I did that from 0 to 10 gigahertz. And afterwards, one thing I really like about RF Pro is that you can just click a button and get a circuit model that you can use in your simulation. So I went back to the circuit and I replaced all those lumped elements with the EM structure, and then I reanalyzed. And looking at the results now, some red flags start to appear. Driving point admittance has a negative minimum value, so I want to run a more thorough stability check of Kurokawa's condition. And to do that, I've got a function here called WSP driving point. This function analyzes any number of driving impedances, and what it does is returns the unstable frequencies in all of those impedances. So I passed both probe outputs to this function, and multiple frequencies got flagged as unstable, both below and above the primary transmit band. So these things warrant some further investigation. Next, I look at the bilateral loop gain, aka the total return ratio, and I saw some high gain sections that roughly corresponded to the unstable driving admittance frequencies. And as a circuit designer, of course, your ultimate goal is to get to the bottom of these loop gain problems. So is this all of the information the probe can tell us? Well, no. The next step is to learn about the directionality of the loop. In other words, does the signal leak from the output to the input, or does it leak from the input to the output? And you'll remember from the presentation, the OSTEST loop gain analysis might be useful for doing that. To emulate OSTEST, I use an equation to process the probe output. This equation is WSP loop gain, and then I pass in the option UNI. This means that the signal will go out of the output side of the probe and it will return back through the input side of the probe. And now looking at the drain loop gain unidirectionally, you can see that just about all of the low frequency loop gain, in fact, seems to travel from the output to the input side. And I can easily verify that by reversing the direction. It's the same equation with the REV option passed in. And that shows very little low frequency gain, in fact, travels in the reverse direction, which confirms our earlier premise. But interestingly, at high frequencies, the loop gain does seem to be more bidirectional, that it travels both from output to input and input to output. So how do you get to the bottom of this? Well, there's lots of ways to do that, but let me show you one technique that I think is pretty neat. What I'm going to do is use the circuit simulation itself to electromagnetically excite the physical layout. And now I'll run an AC simulation, passing in a large signal, but now I sweep frequency, and I do that on the same circuit and EM model that I just simulated with harmonic balance. And after I'm done, I go back to RF Pro, and in the Results tab, I click View Current Density. Now I can excite this layout in a number of ways. I can use ports individually, but instead I'm going to use circuit excitation. And then I go and select the data set from the AC simulation that I just ran. So this will use the circuit results to actually drive the physical layout using the EM tool. Okay, so let's look at 100 megahertz. This is the lower frequency oscillation, remember. Now, if I adjust the color scale, you can see a single spot light up on this layout. This is the bypassing circuit ground, which is clearly coupling the signal across at 100 megahertz. And from the OSTEST, I even know the direction of the coupling. I know that it's going from the output to the input. So this is something that I need to fix in the design. Next, let's go to 3.4 gigahertz. You'll remember this is roughly the high frequency oscillation point. And notice now that the ground plane lights up around the transistor. So this is showing coupling between the matching capacitor grounds. It's actually going from output to input, and it's also going from input to output. And that means I probably just need to add more vias here to improve the isolation. In the end, I modified the design to separate those two bias lines and isolate the grounds, and I also added some resistances to the larger bypass caps to DQ the feedback loops at those low frequencies. For the high frequencies, I added more ground vias below the matching network to improve the isolation. And when I reran the circuit simulation on this and looked at the stability, I can see now the loop gain is well attenuated and the design is in fact stable. And you can also see these effects in the EM excitation. Clearly, when I stimulate the EM structure with the circuit results, the coupling was improved. So I hope this simple example illustrates just how efficient you can be in designing for stability in high-frequency circuits if you have the
All right, so that concludes the presentation portion of this webcast. Just a brief summary. The Winslow probe in ADS is a new way to simplify stability analysis. It allows you to reduce the number of simulation setups and test benches you need to understand stability in your high-frequency circuits. You can get the example workspace with a lot of the earlier examples that I showed you today at the link, which is provided in the Resources tab.
Thanks, Matt. Thanks, Tom. Before we get to the Q&A session, I'd like to call your attention to our survey, which should be displayed to the right of the slides. If that window is not showing on your console, click the icon in the widget bar at the bottom of your screen. The survey is your chance to tell us a bit more about yourself, what your engineering challenges are, and what we can do to help. We also use your feedback for future topics. The survey questions are: 1, how would you rate the overall technical content of today's webinar? 2, after viewing this webinar, do you have a need for these Pathwave Advanced Design System solutions? 3, if you have a need, what would be your time frame?
The F construction, and of course its result. The consequential ability to form the passive network determinant where all the dependent sources have been nullified for normalizing the active network determinant. So I'm a proponent of NDF, but it has some practical challenges. So even if you form the NDF function out of individual return differences, you can still need access to the dependent sources in your network. And when your circuit is composed of complex large EM block simulations with sparse frequency points or active S parameter blocks or symbolically defined devices or closed Verilog models, they can pose problems for the NDF construction and of course its resulting numerical stability. So on the other side of this issue are the loop gain methods, and they can sometimes be notoriously oversimplistic or wrong due to the simplifications required by their construction or the complexity of the circuit that you're analyzing. And they can sometimes provide stability detection that actually differs from the NDF by either false detection or failure to detect an instability in your circuit. In the development of this new probe, it's required a trip through history and duplicating the classic loop gain approaches and studying them against a global method such as NDF or the Atomo method. But at the end of the day, I found that the loop gain analysis approach alone to be very enlightening, but insufficient for too many complex circuits. And then it sort of hit me that the loop gain concept itself is not wrong, it's just incomplete. It needs an associated parameter similar to the Rowlett stability factor has the associated stability measure as an associated parameter. And we're calling this associated parameter for the loop gain, calling it the port impedance or the open loop function. And you can find that in the help pages in ADS under WSP_ZOP. That's ZOP, that's the open port function call that can be accessed. They finally, after all this studying of loop gain methods and the normalized determinant function method for stability analysis, finally I then figured out that these two functions together actually compose the driving point impedance itself. So loop gain analysis can be considered a subset of driving point impedance analysis. And long story short, it gets too complicated, but long story short, I now support the primacy of using the driving point impedance or the driving point admittance as the main stability metric, because it can be shown to be composed of both a function of the bilateral loop gains and the open port impedance function now provided by the new WS probe. So in designs, I track the driving point impedance and the bilateral loop gains together for each probe that's used in the circuit. And as for the designer, all this design for stability power can be utilized and optimized against during the performance and design optimization phase of their circuit design, not after the circuit's been designed or completed, or worse even yet, when it gets to the lab and it starts oscillating. So yes, the WS probe use is technically a local impedance stability approach, but any local method, when you sufficiently spread it through your circuit, effectively becomes global in its scope and its capability for all but the most extraordinary circuits. So short summary, I use the driving point impedance and loop gain provided by the probe for my stability analysis and circuit design.
Great, thank you. What a great answer. Okay, Tom, here is another question for you from Frank. Is the driving impedance from the probe the same one as is used in the STAN tool?
By the construction of the probe itself, they are exactly the same quantity. With the probe usage in your circuit, you don't need any complicated sources for switching or global nodes or anything like that, as commonly shown in the STAN literature. For generating the nodal driving point impedance, which is called H0, that you see in the literature. That function is used for pole zero decomposition to assess local circuit stability. So they are the exact same quantity. So the probe itself automatically outputs a variable called H0, and which is the local driving point impedance. So it was deliberately named H0 because this is commonly used in STAN literature. This driving point impedance can either be saved to a data file or and then analyzed by the STAN tool, or more simply, it can be inverted to form an admittance and then plotted on a polar plot to look for negative real crossovers, which indicate the startup conditions for an oscillation. And for this, you can see Almudena Suarez's auxiliary generator publications and the oscillator theory by Kurokawa. So you don't necessarily need to decompose the poles and zeros of this transfer function to ascertain the local stability of your circuit. So, and the probe works seamlessly from linear to nonlinear analysis. So both autonomous free running and parametric oscillations can be searched. And note that the driving point impedance or admittance itself is easily shown to be the ratio of two network determinants in a similar manner to the construction of the NDF, just using different determinants. And both NDF and the driving point impedance or the driving point admittance share the same network determinant in their respective definitions. So both functions, the NDF and the use of the driving point impedance for stability analysis, are both rigorous quantities for local and global stability analysis.
Great, thanks so much, Tom. And Matt, here's a question for you. This comes from Gunnar. In the demo, why did you use an AC simulation as opposed to harmonic balance to drive the layout?
You can actually use an AC simulation or a harmonic balance simulation to do EM excitations in general. For harmonic balance, it can be a little bit tricky because you need to get the right harmonic mixing term to land on the frequency that you want to analyze with the EM. So in the example, we wanted to analyze something like 3.4 gigahertz. So I would then need to figure out how to drive the circuit at either 3.4 gigahertz directly, or I'd have to do something like 3.4 gigahertz, divided by 3 to get the fundamental somewhere around 1 gigahertz and get the harmonic to the correct frequency. So the short answer is the reason I used an AC simulation in the demo, it's just easier to get the analysis frequencies that I wanted to look at in the EM excitation.
Great, thank you. And here is a follow-up question. What version of ADS is the probe available in, and is it a separate license? Is that required as well?
That should be a pretty easy question. It's available in ADS 2020, and that was actually released last summer in 2019. The probe doesn't require any additional licenses, although I should say you do need to be able to run like a harmonic balance simulation or an S-parameter simulation to generate the data from the probe.
Great, thank you. Okay, we have a lot of questions queuing up, but this will have to be our last question. So this question will be for you, Matt. If you're designing an IC where you cannot access internal breakpoints, is there any good way to understand areas of marginal stability?
Yeah, I assume you're talking about in the lab, which is of course a big challenge, and it speaks to I think why you need to consider stability in the design process, where you can actually get to points that you couldn't otherwise get to if you're like in the lab. One thing that you can do in the lab, and I'm thinking mostly about amplifiers here, is to really look at the small signal response over a large frequency sweep, like outside of your band of operation, and really make sure you're modeling that response well across all of these frequencies. You know, like a lot of times in my experience with power amplifiers, people get the modeling right in band, but then they don't really care that much about the out-of-band response. So as we saw from the demo, the out-of-band response can really be the source of a lot of common stability problems. So don't neglect modeling like the lower frequency response of your design. If you're having stability problems under large signal drive, you might want to look into doing what's called a hot S parameter measurement. You can do that with a PNAX. And that's kind of similar to what I showed today with the OS test example in large signal. Basically, you drive the amp with a large signal in band, and then you can sweep a small signal around that large signal, and you look at the S parameters of that. And sometimes you can see little weird noise or gain spikes out of your band under this large signal drive condition. The trick is, of course, calibrating that large signal out from the small signal, but I can say from experience that the PNAX is really good at that.
Great. Gosh, thanks so much, you guys. Any closing comments from you, Matt?
Yeah, so hopefully in the webcast today we have given you a lot of examples and ultimately simplified the stability analysis process. You know, when you look at the stability for the first time, it can seem really complicated, and I hope this this webcast helped you make sense of that. We've got a lot of great resources for you in the tab, so definitely go check that out, and that's all.
Great. Thanks, gentlemen. A pleasure. This concludes today's webinar. As a reminder, you'll receive an email when the recording becomes available, and don't forget to download the slides now in the resources widget. Thank you for attending today's webinar, brought to you by Keysight Technologies.